Hello and welcome back to G Fun Facts Online, where we dig deep into the science and technology shaping our future. Today we are diving into a story that sounds like it was ripped straight from the pages of a sci-fi novel, but it is actually happening right now in physics labs across the world. It is a story about a resurrection. It is about the material that started the digital age, got fired, and is now coming back to save us from the impending death of Moore's Law. We are talking about the end of the silicon era and the rise of hypermobile germanium. To understand why this is such a massive deal, we first need to look at the engine of our modern world, which is silicon. For over 50 years, the entire semiconductor industry has worshipped at the altar of silicon. It is the bedrock. It is the element that powered everything from those first room-sized mainframes to the smartphone you are holding right now. But here is the hard truth that chip makers have been grappling with. Silicon is tired. It is hitting a wall. We have spent decades shrinking transistors down to the scale of mere atoms to get faster AI and more powerful processors. But we are running out of room. When you make silicon transistors that small, they start to overheat, they leak energy, and, most critically, they are simply not fast enough to handle the data demands of the next decade. The electrons literally cannot move through the material fast enough. This is where the story takes a fascinating turn. Enter germanium. Now, if you know your tech history, you know that germanium is not new. In fact, the very first transistors invented in the 1940s were made of germanium, not silicon. It was the original semiconductor, but it was abandoned in the 1950s because silicon was more abundant and had a more stable oxide layer, which made it easier to manufacture. Silicon was the reliable, steady choice. But in late 2025, a groundbreaking discovery changed everything. Researchers from the University of Warwick and the National Research Council of Canada announced that they had essentially supercharged germanium. They engineered a new form of strange germanium that absolutely shatters the speed limits of electricity. We are not talking about a 10% or 20% improvement here. This is a complete rewriting of the rules of electron transport. Let's break down the numbers because they are mind-blowing. In the world of semiconductors, the most important metric is something called mobility. Mobility is essentially the speed limit of the material. It measures how quickly an electrical charge can move through the chip when you apply voltage. To give you a baseline, standard silicon has a mobility rating of about 450 centimeters squared per volt second. That is decent, it is reliable. Think of standard silicon like a family sedan driving down a suburban street. It gets you there, but it is not winning any races. Now compare that to the new material developed by these researchers, which they call compressively strained germanium on silicon, or CS-GOS for short. In December 2025, they demonstrated a mobility of 7.15 million. Yes, million. Standard silicon is 450. This new germanium is 7 million. If silicon is a person walking down the street, this new hypermobile germanium is a fighter jet screaming past at Mach 10. It is a difference of thousands of times over. So how on earth did they do this? How do you take a material that has been around for decades and suddenly make it millions of times faster? The secret lies in something called strain engineering. Imagine a layer of germanium atoms. If you leave them alone, they sit comfortably in a crystal lattice structure. But the researchers didn't leave them alone. They grew this layer of germanium on top of a silicon lattice. Now, germanium atoms are naturally larger than silicon atoms. So to fit onto the silicon floor, the germanium atoms have to squeeze together. This squeeze acts like an atomic corset. It applies massive compressive strain to the germanium layer. This pressure drastically alters the quantum mechanical properties of the material. It smooths out the energy bumps that usually slow down the electricity, creating a near-frictionless highway for charge carriers. And the best part? They achieved this in a way that is compatible with current manufacturing. They grew this nanometer-thin layer of super germanium directly on a standard silicon wafer. This is huge news for the trillion-dollar semiconductor industry because it means they do not have to throw away their factories. They can upgrade them. Now, we need to get a little technical to appreciate the genius of this solution. In a modern computer chip, which we call CMOS, you need two types of switches to make logic work. You have the N channel, which uses electrons to carry negative charge, and you have the P channel, which uses holes to carry current. A hole is just the absence of an electron acting like a positive charge. Historically, holes are the sluggish ones. They are the slow lane of the highway. This has always been the bottleneck in chip design. The record-breaking 7 million mobility number I mentioned earlier, that specifically applies to holes. This is a total game changer because it turns the traditionally slow P channel into the fastest part of the chip. But that leads to the next question. What about the electrons? If the P channel is now a Ferrari, we can't have the N channel acting like a bicycle. While compressive strain supercharges the holes, researchers needed a different trick for the electrons. This is where a material called germanium-tin comes into play. By adding tin to germanium, or by pulling the atoms apart with tensile strain rather than squeezing them, researchers are creating complementary hypermobile N channels. Recent data shows that germanium-tin transistors can achieve electron mobility 2.5 times higher than pure germanium. So the vision for the chip of 2030 is a hybrid architecture. You will have vertical transistors, where the P channels are made of ultra-fast strain germanium and the N channels are made of high-speed germanium-tin, all sitting on a silicon base. It is the best of all worlds. But wait, there is more. This breakthrough is not just about making your smartphone faster or your gaming PC more powerful. Hyper-Mobile Germanium acts as a key that unlocks the future of quantum computing. We talk a lot about quantum computers on this channel, and usually, we are talking about massive machines from Google or IBM that require giant cooling infrastructures. But the holy grail of quantum computing is the silicon-based spin qubit. These are qubits that look and feel like tiny transistors, which means we could print them by the billion using existing factories. It turns out that germanium is far superior to silicon for this purpose. There are two main reasons. First, there is a property called spin-orbit coupling. In silicon, if you want to control a qubit, you often need bulky micromagnets to create a magnetic field gradient. It is messy and hard to scale. Germanium, however, has strong spin-orbit coupling. This allows the qubit to be controlled purely electrically, using simple voltage pulses. It is faster, simpler, and much easier to scale up. Second, remember those hypermobile holes we talked about? It turns out that hole-spin qubits in germanium are exceptionally stable. They have long coherence times, meaning they hold their quantum state longer. So the exact same material that makes classic chips faster also makes quantum chips more feasible. We are looking at a future where a single chip could host high-speed classical logic and a quantum coprocessor, both built on the same germanium on silicon platform. So the big question is, when can you buy one? When does this leave the lab and enter the fab? The industry roadmap, driven by giants like TSMC, Intel, and ASML, suggests a transition period between 2028 and 2032. Right now, we are moving from FinFET transistors, which are the little fins inside current chips, to gate-all-around nanosheets. The step after that is the CFET, or complementary FET. This is where N-type and P-type transistors are stacked on top of each other to save space. This is where germanium is expected to shine. The plan is to use silicon for the N channel, where it is still very good, and strain germanium for the P channel, replacing the sluggish silicon holes. The goal is to have a trillion transistor processor by 2030. Of course, it is not all smooth sailing. There are significant engineering challenges. The biggest one is the thermal budget. Germanium-tin alloys are very sensitive to heat. If you get them too hot during manufacturing, specifically above 500 degrees Celsius, the tin atoms can clump together and ruin the crystal. Since chipmakers love high heat for reliability, they have to invent entirely new cool manufacturing processes. There is also the issue of defects. Growing germanium on silicon is like trying to tile a floor with tiles of the wrong size. If you are not careful, the strain snaps the crystal, creating dislocations that kill the chip. The Warwick and NRC breakthrough is so significant precisely because they managed to keep the crystal ultra-clean despite the massive strain. We often hear people say that Moore's law is dead. And that is true, but only if we stick to silicon. Hyper-Mobile Germanium proves that we aren't running out of physics. We were just looking at the wrong map. By looking back at a material abandoned in the 1950s and applying 21st century nanotechnology, we have found a way to break the speed limit. The chips of the next decade won't just be smaller, they will be made of fundamentally different materials. They will be strained, alloyed, and engineered to let electricity flow like water down a slide. The Silicon Valley of the future might well be nicknamed Germanium Valley. That is all for today's deep dive. Thanks for listening to G Fun Facts Online, and make sure to subscribe for more updates on the science that is building tomorrow.